all the area, because the alpha refers to the area. Yeah, when it's one tail, you concentrate all the confidence in one side only. But when you have a two-tail test, you have to split. You have to split the confidence into two half. One on the left-hand side, the other on the right-hand side. That is the reason just now, if you remember example 1 and 2, we take the 0.05, I divide by 2 so that we get 0.025 because we have to half it to the left and right. Okay, so the key point here is if greater than or less than is one tail test. If equal is always two tail test. And then what is the impact? You take the alpha divide by 2. That's one thing you must remember. And then okay, and then hypothesis is greater than value. Then you take the left tail. Then you take the right tail. Okay, so let's look at the left tail first. Now, look at the area. Look at the area. The critical value is the point where the area stops. So if I put my laser pointer, this is where the critical value is the x-axis value at this point. Okay, so this is the critical value for the first graph. Then the second graph, the critical value is here. Then the third graph, it has critical value on the left and right. It has critical value on both sides. So usually we can use either one. That's why we use the absolute value, we ignore the negative. Okay, so okay, back to this critical value. You say, let's look at the first one, the left tail test. Now, which side is bigger? This side to the left of the critical value or the one to the right of critical value? Apparently to the right of critical value, right? So the one to the right of critical value means that we are very confident. Yeah, we're very confident because the significance value is big. If to the left, then the significance value is small. Yeah. So that is why when we are confident, we don't reject the null hypothesis because the null hypothesis is correct. You see, if the calculated value that we have, is to the right hand side of the critical value, that means it's bigger, then we're actually confident. We are confident with our null hypothesis, so we cannot reject it. It's only when the z value, the calculated z value is less than the critical value, that means it's on the shaded, right? It's shaded. That means our confidence is less than what it's supposed to be. That one we have to reject the null hypothesis, right? So if it is a right tail test, if the z value is bigger, is it opposite already? If z value is bigger than the critical value, that means the area is small, right? The area is small, then we have to reject the null hypothesis. So whether bigger or less than, in order to reject the null hypothesis, try to map it out to the graph. Then you see if your z value is in the white area, you accept the null hypothesis. If it's in the shaded area, that means less than the critical value, you reject it. Now, what about if it's two-tail analysis? If two-tail analysis, right? If the critical value is less, sorry, if the calculated z is less than the critical value, again, what is critical value? Critical value is this point. You see my laser pointer. This point on the positive side, and then again another one, equal one on the negative side. So it is the value that is the z value that actually become the boundary that separate the shaded and unshaded area. If your calculated value is to the right of this critical value or to the left of the negative critical value, that means you're not confident with your null hypothesis, you should reject it. But if the value happen anywhere along this area, then you should accept the null hypothesis. You cannot reject it. All right. This is how you visually decide whether to see greater than or less than in order to accept or reject the null hypothesis. I hope that makes it clear why sometimes we look at less than, sometimes we look greater than. It depends on the question. And I think the best way to understand is if you can visualize this. All right.